All right, HL folks, we got our Chapter 8 review here. And in this video, I'm just going to kind of scroll through and make some general comments and hints and suggestions. And then I can make some more focused videos going through problems step by step as needed. When we're finding the area of the regions, what you're going to do is find where your graphs intersect and then do the integral of the top curve minus the bottom curve from A to B. So basically from your two intersection points to each other. So set your curves equal and go from there. Same idea with all of these, just finding where they intersect and doing the integral of the top curve minus the bottom curve. When we get down to the differential equations, that's where you need to think if you are able to separate the variables, or if it's a homogeneous equation, or if it's an exact equation. So just real quick as I look through them, part A is separable. You just want to multiply by x plus 1 and divide by x. Or excuse me, the other way around. You want to divide by y and multiply by dx, because then your y is with your dy. On part B, it's also separable. You just need to multiply by dx. On part C here, let's see, are we able to separate those? It's not really looking like it. What you can do on part C then is if you divide both sides. Let's take this one a little bit here. So I'm going to subtract 1. So x y prime equals y squared minus 1. Okay, we're actually in business. This is separable as well. So if I divide both sides by y squared minus 1, I can get dy over y squared minus 1. And if I divide by x, I can get 1 over x and multiply by dx, like that. And so it is separable as well. It just took a second to show itself to me. The left side, you can use partial fraction decomposition and then have it be the sum or difference of two logarithms. So part C is also separable. That's great. Let's see, part D. Yeah, I think that one's going to be separable as well, because you can write this as 1 over y times x plus 1, and then multiply both sides by y. Okay, looking at part E. Okay, this one is not separable because you've got your x's and your y's kind of mixed together with it. And so this one would look like, to me, this would look more like an exact differential equation. And so if it's an exact differential equation, that's when you want to choose the function that is attached to the y value there and write your integrating factor e to the integral of 2 over x dx. And if you multiply everything by that, then you would get a product rule situation on the left side, and then on the right side you just have to integrate sine of 2x and x squared normally. So that one is an exact differential equation. Let's see, what about f? F also looks exact to me because we would multiply by e to the integral of tan x, and looks the same. You could do the same exact equation on G as well. So I'm not seeing any that are homogeneous at this time. So separable and exact. All right, moving on along. Here, you should get really used to reading differential equations with the word proportional. So when it says is proportional, you know you're going to write is for equal, equals for is, and then proportional to the amount that's left, y. So get used to setting those sorts of things up. All right, scooting on down. That one is solvable. It's separable. You have your initial conditions. Nothing too much there. On number 6, you've got Euler's method here, and so you know y of 0 equals 1, and you have a step value of 0.25, and so you're just using that to get the next x value, and you're using tangent lines to approximate the next y value. And then when you sketch the graph and when you solve it analytically, then you should be able to compare, was your estimate an overestimate or an underestimate? Like, was it above the curve or was it below the curve? Solving this thing analytically, you might want to use probably an exact equation there. If you move this term over to the left side and then do the e to the integral of the function, you'll be able to solve it like an exact equation. Okay, moving along. Maclaurin series, you need to take a bunch of derivatives and then plug in x equals 0 and construct your Maclaurin series that way. When you look at problems 8 and 9, those are probably L'Hopital's rule situations. You always just try to plug in 0, but you're going to run into a lot of 0 over 0. And so, like on problem 8, if I plug in 0, I get 0 over 0. And so then I just take the derivative, cosine x minus 1. The derivative of the bottom looks like a product rule, so sine of x plus x cosine x. Unfortunately, we're still at 0 over 0, so we do another L'Hopital's rule, and we get negative sine x over cosine x plus cosine x minus x sine x. And at this point, you can plug in 0 again, and I think you get an answer of 0. I did that a little quickly, so there may be a mistake in there, but that's the big idea. Moving along, we already talked about areas between curves. Distance formula is not too bad. Let's see. I think those are the big ideas. Of course, some of these problems, get pretty tricky as you go down, so I'll make some more focused videos of those. But that's the overview of the chapter. Thanks for watching. Ask if there's anything more I can give you.